Hello everyone, so welcome to the second video for this week. So I'm going to do things in a bit of a different order than what's in the PDF notes. Try to give it a little bit more logical flow. And eventually we'll do everything, so don't worry. But I'm going to skip ahead to some of the material on page 4 now about the first derivative test, because that fits in quite nicely with what we were talking about in video 11 about relative max and min. So let me just remind you, so this is the topic, is first part of our topic today is going to be finding relative max and min. So let me just remind you what they are. So relative max of a function y equals f at x is a point, say a f at a, which is larger for which, should say this way, for which the value of f of a, we have a visitor, he wants to learn about relative max apparently as well. He was having a long nap, so he's gotten up for class, that's great. For which the value of f at a is larger than all the values of x when x is near a. So let me just kind of draw the picture. The picture speaks 1,000 words, right? So this is kind of at the top of a mountain, basically. Puccini is really in the way right now, but he'll go down eventually. So relative max would be here, this point AF of A, that's a relative max. Right, the values of the function are smaller than the value of f of a so long as you're near f of a. So it's kind of like a mountain peak, right? A mountain peak of the function, if you want to think of it that way. It may not be the largest value of the function. We talked about this, right? The function can keep going, and you could have an absolute maximum somewhere else. But it's like, you think about locally near the point A, f of a is the largest value, and so it's like a little peak there, and that's the relative max. Similarly, a relative min, I won't write it all out in words, would be like this point here. Looks like roughly it's at 0, some f at 0, and it's the smallest point, right? It's the point that's the smallest point near it, around it. So precisely. There's a precise way of defining a neighborhood in mathematics. This might surprise you, but you can think of it quite intuitively, like around or in a neighborhood of that point, the value at 0 here is the smallest value, right? The function comes to a little bit of a valley there, and then moves on. But it need not be the smallest value the function ever reaches. Later on, at some other point, the function could be much lower. But we don't care. Relatively speaking, around this point, this is around the point 0 here in purple. This is the smallest value the function attains. So this would be a relative min. Okay, so the question was, so you can see these from the graph, right? We can see on the graph how to think of a relative max and a relative min. And the question now is, how do we actually find these guys using calculus, right? So what I was saying in the first video at the beginning is like, we can learn how to read things off a graph. We do this a lot in pre-calc, and we do it here a little bit again in a little more precise language. But I mean, we're not in this class to read things off a graph, because you can't assume that you have a graph all the time. So we want to eventually get to the point where we can know everything or a lot of things about the graph of a function from just the formula, from just algebra. And that's where the calculus comes in handy. And so what I ended the last video on was kind of thinking about where what's happening at a relative max or relative min in terms of calculus. So here's the question I want to answer first today. How do we find the relative minima or maxima of a function using calculus? So, and this we can kind of just do like a thought experiment, right? From the graph does tell us a lot of what we should be looking for, right? So just if you kind of think about taking this part of the function here and blowing it up, we can answer quite a bit about what's happening at a relative maximum. So this would be the rel max. And notice that as we're coming in, I'll use a different color maybe. If we look at the tangent lines to the function, the tangent lines to the function as we approach the relative maximum have positive slope, right? So, but they get less and less positive, and actually at the peak of the mountain, right where the maxima is, right, we have a flat tangent line. When you're standing on the mountain peak, you're no longer ascending the mountain. Then when you pass the peak, the tangents, that's a bad tangent. The tangents begin to have negative slope, right? So the function begins to decrease after on the right of the maximum. And if I can draw a proper tangent line here, Puccini, you are really kind of messing things up right now. Okay. Okay, so to the left of the max, we see that the tangent slopes are positive, and that's the same thing as saying the derivative is positive. And to the right of the max, the tangent slopes are negative, the derivative is negative. And exactly at the max, f prime at a is 0. We have a flat tangent line. If you're on the top of the mountain, you're not climbing anymore. The immediate tangent is flat. You're just sitting there and enjoying the view, hopefully, or having a snack or something, taking your pack off, whatever you need to do to chill out for a few minutes. But you don't have to keep climbing up. At the top of the mountain, the tangent's flat. So this is it. This is the first derivative test for a relative maxima. So for a relative minima, you can imagine what's going to happen, right? So this is a big bowl here. So as they say, that's the minima, right? As you approach the minima, you're descending. So the tangents are all negative. I'm having a bad tangent day today. Okay. Oh, I know what's going on. Pen there, screwing it up. So this derivative is negative. At the minima, at the bottom of the valley, you're no longer walking downhill, right? The tangent line will be flat there. And as you climb out of the valley, you start walking uphill, steeper and possibly steeper and steeper. So your tangents start becoming more and more positive. And the first derivative is positive there. The function is increasing. And so these pictures, so this is the rel min case. These pictures tell us exactly what the first derivative test is. Okay, so I'll put this into words now. So often the hard part, I think, of this section is a little bit putting these ideas from the graphs that you kind of see visually very intuitively into precise mathematical language. But once we've done it, we can use it and it's quite straightforward. So here we go. So first derivative test. We're calling them relative max or min. Okay, so suppose, here's the first part. Suppose x equals a is a point for which the derivative at a is 0. So you notice that that happened in both cases, right? Whether you're at the top of the mountain or you're at the bottom of the valley, your tangent line is flat there. Okay, so that's condition 1. Part 1. So if f prime at x changes from positive to negative as we move from left to right across the point A, as we move from left to right, across the point x equals a, then clean it up a bit. Then AF at A is a relative maximum. So that's exactly what I was saying in this first picture, right? Two, if f prime at x changes from negative to positive the other way, as we move across the point A from left to right, then AF at A is a local minimum, or relative minimum, sorry. Just want to keep using that word local, but minimum. Not parentheses here. Okay, so that was exactly this second picture. You're walking down into the valley, you're walking downhill, the slopes are negative, they get less and less negative as you get to the bottom. At the bottom, it's flat and you start climbing back up, getting steeper and steeper on the other side. So you go from, f prime goes from negative to positive. Now, there is a third thing that can happen that I didn't mention to you, but you should be aware of because you will see it. If f prime at x does not change sign as we move across A, x equals A, then the point AF at A is neither a local min nor a local max. Okay, so you might be, okay, this we haven't quite talked about. So when does this kind of thing happen? So for example, you can have the function y equals x cubed. Which looks like this. And you look at the point 0. Right, so I can kind of blow this up a bit for you. So at the point 0, you actually have a flat tangent line. So f prime at 0 is 0. And that shouldn't be a surprise, right? Because, zoom out for a second. Because, you get y prime is 3x squared, right? So y prime at 0 is 0. But look, you can see both from the formula for y prime and from the graph that this is always an increasing function. Right? The derivative is always non-negative for this guy, y equals x cubed. And you can see that you don't, like the value f at 0 equals 0 is not the smallest value around it, nor is it the largest, right? They're both smaller values and larger values on either side of 0. So this is not a relative min or max. It's something else. Something else is happening there. And I will talk about that in a little bit. So the point 0, 0 is neither a min nor a max. In fact, f prime at x equals 3x squared is greater than or equal to 0 for all x. So f prime at x does not change sign on either side of 0. Okay, now something else is going on there, but we'll deal with that in a bit. So this gives us, like this first derivative test gives us a very nice way of finding local max or min, a relative max or min, right? You look for a point which the derivative is 0, right? And we can do that using some algebra, and now we know how to take derivatives, so we're going to be good. Because if you have a max or min, right, the tangent line has to be flat there, as we saw in these pictures. And then you just see how does the sign change as you go across the sign of the derivative change as you go across the point A, right? If it goes from positive to negative, you have a max, and if it goes from negative to positive, you have a min, and if it does not change, then you have nothing. Well, not a min or a max, you might have something else. Okay, so this is, I said, a straightforward thing, but we should practice implementing it. So let's do it. So this is an example. I'm taking off the homework rather than the notes because the notes did not have any good examples of the first derivative test, which was really surprising. So this is the homework from section 2.3. It's number 2. And again, your exact question might be a little bit different, but numbers should be roughly similar idea. Okay, so the graph of the function f of x equals 4x cubed minus 48x has one local min and one local max. They actually are using the word local instead of relative. So has one local, a relative, min, and one local or relative max. Find these points using the first derivative test. Okay, so here we go. So first, we need to find the points A, F at A, or just such that F prime at A equals 0. So to do this, we compute F prime at X, and then set F prime at X equal to 0 and solve for X. Clean that up a bit, right? Because remember what I was saying, if you have a min or a max, then the tangent line has to be flat there. The derivative has to be flat there. And this test that we developed, first derivative test, right? The first thing points for which the derivative is 0. Right? Okay, so in our case, this isn't so bad. So we can just use the power rule. So f at x is equal to 4x cubed minus 48x. And so f prime at x is equal to 12x squared minus 48. So now we set f prime at x equal to 0 and solve. So we have 12x squared minus 48 is 0. And then we can take that and factor out 12. So you get x squared minus 4 is 0. And this factors very nicely. So we have 12 x plus 2, x minus 2 equals 0. And hopefully you remember that's your difference of squares factoring. And so now we can solving for x, we have x equals 2 or minus 2. Okay, so now we need to apply the first derivative test to the points 2 and minus 2. So now we need to apply the first derivative test to the points s equals 2 and minus 2. Excuse me. And there are different ways of doing this, of checking the sign on either side. So what I like to do is I like to make a table. The book will tell you to make a number line, the help, whatever the heck it is. That's fine too. If you like that better, that's fine. I'm gonna give you a different method. I don't draw very well, as you know. So for me, number lines are kind of get very cluttered very quickly. So here's how I do this. So to apply the first derivative test, I like to make a table. I'll try to make the table on one page. So what I do is I have one column. So the first column is the intervals, where I'm checking the sign of the derivative f prime. So what I do is I look at the lowest point where the derivative is 0. And so we're gonna have to check the sign to the left of minus 2. And then, then we'll have to check the sign of the derivative between minus 2 and 2. So to the right of minus 2, but to the left of 2. So the next interval I have is going to be, this is for the next row. It's going to be x is between 2 and minus 2. And then we'll have to check the sign of the derivative to the right of 2. So the next row is going to be x larger than 2. And so those are the 3 rows in this case. Okay, now for the columns, I'm going to use the factorization of the derivative here, because the sign of the derivative, right, is the product of the signs of its factors. So this will be the sign of the first factor, x plus 2. This will be the sign of the next factor, say x. You can throw the 12 anywhere you want. 12 is positive, it won't affect the sign. sine of 12x minus 2, and this is the sine of f prime. And then what I do is I have kind of the last column is local max or min. So I'll just write, okay, so now what? So remember, let me just write here. So the derivative, if you remember the derivative, it's kind of up there. There it is. Here it is, but I'll write it downstairs so you see it. So it's 12x plus 2, x minus 2. And what are we doing? Okay, now we're gonna try to figure out if the sign of this guy, the sign of the derivative, changes as you move across each of these points where the derivative is 0. And how it changes will determine whether the point we're dealing with is a local min or a local max, or perhaps not neither. Although we're told that there is at least one of each, so they have to be one or the other in this case. So now I want to figure out the sign of, so this column here, this entry of the table here, and I'll do it in red if you like, is the sign of this factor x plus 2 for when x is below minus 2. So to figure out the sign of the factor x plus 2 when x is below minus 2, we just need to plug in our favorite number below minus 2 into x plus 2. So say minus 3, for example, is less than minus 2. If I plug in minus 3 to x plus 2, I get minus 1. Minus 3 plus 2 is minus 1, so this is negative. So maybe I have too many red lines. So this is negative. So now we plug in our favorite number, again, below minus 2 into the factor 12x minus 2. And we just don't need to worry about what number that is. We need to worry about the sign, right? So if we plug in minus 3 to x minus 2, right? We get minus 3 minus 2 is minus 5. That's negative. Multiplying by 12, it's still going to be negative. So this is negative. Now, to figure out the sign of f prime, I just read across the row, multiplying signs. But this is the beauty of this system. Minus minus is positive. And that's exactly why I do it this way, because, right, why I set up the table this way, because f prime is a product of these factors, so the resulting sign is a product of the signs of the factors. So you just can read it off by multiplying signs across the row. So that's a plus. So I'll do the next row, and then you can do the last. I'll tell you what it is, but you should figure it out for yourself. Okay, now here we need to figure out the sign of the factor x plus 2 when x is between minus 2 and 2. I'll let you out in a bit. We're in the middle of the problem, okay? Don't cry. So we plug in our favorite number between minus 2 and 2, which my favorite number between minus 2 is 0. We plug in 0 to this guy, we get 2, which is positive. We plug in 0 to this guy, we get 0 minus 2 is minus 2, negative. Times 12 will still be negative, so that's negative. So reading across the row, positive times negative is negative. So now I can fill in this last column. So as we move across minus 2, reading down this column now, as we move across minus 2, the sign of f prime switches from positive to negative. Positive to negative max. So x equals minus 2 is max. So I just write it there. So I don't know, I love this table. It takes a little more writing than the number line way, but I think the method is clear. So I'll fill out the last row here, and you can do this. This is positive. This is positive. So that's positive. So then minus to plus is a min. And there we go. Finito. Okay, so I'm going to let the cat out of the room. And while I'm doing that, you should contemplate this and what how I got the last row, okay? Okay, so I'm back. So sadly, The first derivative is not enough to completely understand the function. And the example of x cubed that we saw when discussing the first derivative test, I think indicates that there's more going on. So, oops, sorry, let me get it there. So let's go to the next page maybe. So sadly, the first derivative is not enough information to produce the graph of a function f of f of x from its formula. There's a couple of ways to think about this. So if you look on, what was the example that's not a great example. Let me do another one. Okay, so for example, consider the following functions. So this first function I'm going to give you is root x. And the next one I'll give you, so I'll call this, I should give this a name, we'll call it f at x. And the next one I'll give you be g at x. And now this is going to be something we'll see later, but it's like 2 to the x. So something like that. Clean that up a bit. It's a bit better. Okay. Now, both of these functions are increasing. They both have derivatives that are positive. So f prime at x here is positive for all x, and here g prime at x is positive for all x. Okay, we know how to actually compute the derivative of this from the power rule. This, we don't know how to find the derivative from the formula yet. We'll do it eventually. But you can see from the graph, if you believe me, this is what the graph is, that is positive, right? Derivative is positive. But you should notice that like these graphs are very different, right? They're both very, very different. So that's one problem. Like the first, we have positive first derivative for both of these guys, and the graphs look totally different. So even though, f at x and g at x have positive first derivative throughout their domains, their graphs are very different. Okay, so we need to kind of take a deeper look at these graphs here. So let me hope now Petrini's gone from the room, so he won't be getting in the way of me drawing tangent lines. And there was a cord underneath the iPad, so it was causing it to move. But so hopefully I can not goof this up. Okay, so those are some 3 random tangent lines for the root curve. This one could be a bit better. There. I'm going to draw 3 random tangent lines here. Okay, so if we look at these situation with the tangent lines and these 2 graphs, we see that they are very, very different. Here, for the root curve, the tangent lines start out large and positive, right? So there's a very large positive slope here, it's very sharp. And then the slope tends to slowly flatten out. On the other hand, if you look at the exponential, it's 2 to the x, right? So here the tangent line is positive, but almost flat. Here it's more positive, and here it's even getting more positive. So what's happening here? So in this example, in the root curve, the slopes of the tangent lines are decreasing as x increases. Slopes of tangent lines decreasing as x increases. On the other hand, let me move this jazz down here. For the exponential graph, the slopes of the tangent lines are increasing as x increases. Oh, okay. So let's think about what is that saying about our function in calculus terms? So the derivative, right, f prime, the first derivative, is measuring the slopes, right? This is the function of slopes. In the first example with the root curve, those slopes are decreasing as x increases. So that means that this function here is a decreasing function. Oh, it's a decreasing function. So that means its derivative, namely the second derivative of f, must be negative. So let me write that down. So unfortunately, I can't put that on the same page. For f at x, slopes of tangent lines decrease. So that implies f prime at x is decreasing function. And that implies its derivative, which is the second derivative of f, the derivative of the first derivative, is negative. And we say, this is another definition now, this implies f at x is what's called concave down. Because it's bending downwards as you move in the positive x direction. So it's like this chain of logic is quite important. I'll do it for the other one too. I'll do it for the g. Okay, now for g, the slopes are getting more and more positive. So the slopes are increasing as x increases. So the functions of slopes, which is the derivative of g, must be an increasing function. So its derivative has to be positive. So that's saying the second derivative of g has to be positive. So we write that down here. For g at x, the slopes of the tangent lines to g increase as x increases. That implies that g prime of x is an increasing function. And that implies that its derivative which is the second derivative of g, so the derivative of g is positive. And then we say g at x is concave up, because it's bending up as x increases. Okay, so now I can determine these two graphs apart by looking at their second derivative. So though the first derivative on both of these is positive, this has a negative second derivative, and it's concave down, which I'll just say CD, concave down. This has a positive second derivative, and it's concave up, CU. Okay, so the point is that the first and the second derivative, so generally is enough information about the function to be able to draw a rough graph. If you know the signs of the first derivative and the signs of the second derivative, you can basically draw a rough sketch and find where the max and min are, the relative max and min or local max and min. The higher derivatives do have information, more information, obviously, like the third derivative and fourth derivative would have more information, but that information is not so easy to see with the naked eye. If you're really interested in one of the Zoom meetings, I can kind of tell you a little bit about what the higher derivatives are saying about the shapes of the graphs, but it's unless you have a very good resolution computer type thing, you're not going to notice what they're saying anyway. And at that point, you probably wouldn't do it by hand. So for most applications, you don't need that information yet. Okay, so I'm not worried about it. So in general, we can draw a rough sketch of a function from information, from info, about its second and first derivatives. So I should be a little more formal and explain to you a little bit more about the second derivative. Okay, so the second derivative and concavity. So let fx be a function. Then the second derivative I'll write it this way. F double prime of x measures the concavity of the function f. It measures the concavity of f. If f prime at x is positive, then f at x is said to be concave up. I'll just say CU. And so that means the tangent lines are increasing. The slopes of the tangent lines are increasing as you move from left to right along the graph, i.e. the slopes of the tangent lines to f are increasing as you move from left to right. Now, there's a number of ways in which this can happen. So just some examples. So there was the root curve, right? That's okay. So that's one example, but it doesn't have to be, the function doesn't have to be increasing to be concave up. You can also have a decreasing function that's concave up, or parts where the function is decreasing and concave up. So if you look at the parabola, for example, it's not a good parabola. So if you look at the tangents to the parabola, if you're over here, you have some large negative tangents. But as you approach the vertex, they get less and less negative. At the vertex, there's the tangent 0 at the local min, and then they get more and more positive as you move away. So this is kind of like, so here, f prime is less than 0, f prime is greater than 0, but the whole time, f double prime is positive. And this is concave up, because the tangents are constantly getting more and more positive as you move from left to right. They start out really negative to get to 0, more and more positive. So this is concave up. If f double prime at x is less than 0, then f at x is concave down. And the tangents of f at x decrease, the slopes of the tangents, the tangents of f at x decrease as you move from left to right. I.e. f prime at x is decreasing. So that's like, that's like the root curve. So this one I didn't even do. This I meant to do the exponential here. So this is y equals 2x concave up. So here, this is like the root curve. Tangents getting flatter and flatter. What's another good example that you might see? You would know. I guess just a kind of a lame example is something that's concave down is an upside down parabola. So y equals minus x squared. So with y equals minus x squared, right, the tangents to the negative side of the origin start out really big and positive. They become less and less positive. They go, and the tangent is 0 at the max, then starts getting more and more negative. The graph is bending down. So here you have f prime positive, f prime negative, but the whole time it's negative, it's concave down. Okay, so that's the idea of concavity. It's how it's the derivative of the first derivative. It's how the tangents are increasing or decreasing as you move from left to right. So f prime is a decreasing function here. And like I said, the root curve is concave down. Sorry, I drew it here. The exponential is the one I meant to draw. Is concave up. But you can have a function that's concave up and increasing, or it can be concave up and decreasing and increasing for some time, like the parabola, and the same thing with concave down. Okay, now also to throw another little wrench in the works, you can have, a function does not have to have the same concavity over its domain. So to complicate things, a function can change concavity in its domain. I.e., go from being concave up to concave down, or vice versa. And what's a good example of this? Well, our friend y equals x cubed that we saw had this weird behavior at the origin. Okay, now let's bend this around a bit. There, that's better. Now look at this, right? So if we look at the tangents here, on the negative side of the origin for negative x, we see they're starting off positive and getting flatter and flatter until you get to 0, which we saw had a flat tangent. It's like, but the graph doesn't bend down at 0, it bends back up. So now you see the tangents as you move to the right of 0 get more and more positive. So here we have a situation where f double prime is less than 0 to the left of the origin, and it's greater than 0 to the right of the origin, right? So for y equals x cubed, f double prime of x is negative for x less than 0, and f double prime of x is positive for x greater than 0. And the graph changes, or switches, I should say, from concave down to concave up at x equals 0. So a point where the concavity of the graph changes, whether from concave up to concave down or vice versa, is called an inflection point. So definition, a point where the concavity of f at x changes. Doesn't matter how, one way or the other, i.e. f double prime at x changes sign around the point is called an inflection point. Of f at x. So now I want us to kind of do some maybe visual examples of trying to see if we can figure out from the graph, if we can figure out concavity from graphs, and then and read out and find graphically the inflection points like we did for x cubed. But I need to switch to the other app, so give me a moment. Okay, so I've switched the notes to the PDF. There's a bit of a delay, but hopefully we can kind of talk through this. All right, so look at this. I want to look at the first graph, which we discussed last time in a bit of a different context, right? We were talking about relative min and relative max. We want to figure out where is this graph concave up, concave down, and are there any inflection points? So where the concavity changes. So let's start along the graph at the very, very left point. And we notice that the graph is bending up, right? We start off with some negative tangents. We get to a 0 tangent at -2, 1. Then we get more and more and more positive tangents, right? But as we cross, sorry, so as we cross 0, 2, we see that the graph begins to bend down, right? It bends down. Let me the note switch there for a second, but it bends down as it goes to the maximum where you have the top of the mountain. It continues bending down until you get to 4, 2, right? And then it begins to bend back up. The tangents begin to get more and more positive as we get down to 6, 1, where we have a min, and then it continues being positive. So I can summarize by that by saying it's concave up from the left endpoint to 0, 2. Then it's concave down till 4, 2, and then it's concave up the remainder of the way. Delay is not too bad there. And then we have 2 places where it inflects, where you kind of get here you get a maximum positive slope at 0, 2, and it starts bending down. So this is an inflection point, 0, 2, inflection point. And here at 4, 2, you get an inflection point. So you have kind of a maximum negative slope at 4, 2, and then it starts bending up. So we have 2 inflection points. Okay, so that's all I'll do for this video. Try to do, this is a great example. Try to do this one, this next one on your own. And if you have trouble, we can definitely talk about it on our Zoom, on our live Zoom session where we'll all get together. It's a very, very good question because it tries to get you to understand the difference between F being positive, F prime being positive, and F double prime being positive, and how all these 3 different things can happen in any which way in the domain of the function. Okay, so I won't do much more about that. We'll talk about that at the live meeting. And the next point for me is to show you how you can use this information, the information of the first and second derivative, to draw a pretty good rough sketch of the function. All right, thanks for tuning in.